Hello, and welcome to the Preparatory workshop for the Part 3 Foundations courses. So this video will be on the axiom of choice. Okay, so we saw in the previous video the other axioms of ZF. The next one that completes ZF to ZFC is the so-called, the very famous axiom of choice. So here we'll see the formal, first of all, formulation of it and several equivalent statements. Okay. So what does it say, first of all, intuitively? So we say that if S is a family of sets such that the empty set is not in S, then a choice function for this family S, it is simply a function on our set S with a property that for every element x in S, f of x is a member of X. Okay. So the way that you can sort of pictorially think about this is that we've got our family S. So our family S has all of these sort of red sets that I've drawn here. And a choice function is simply a function that selects for each one of these members an element from it. Okay. And of course, in order to select an element, it must be that all of these are non-empty, hence our assumption that the empty set is not in this family. Okay, so the classic example to this that might make it slightly more intuitive is that suppose that you have a collection of pairs of socks. A choice function for that collection would simply be a function that for each pair of socks would select one of these two socks. Okay. And what the axiom of choice will tell you in this context is that there is a way from this collection of socks, of pairs of socks, which could possibly be infinite, there's a way to always make a choice and to always select from each pair one of the two socks. You might think that this should be provable from the other axioms of ZF, but in fact it is not, and it is a highly non-trivial statement. So first of all, let's see how to formally express this. So the statement, once again, is that every family of non-empty sets has a choice function. So how do we say this formally? First of all, we say that for all S representing the family, provided that S has non-empty sets, so all elements of S, so for all X in S, X is not equal to the empty set. Recall that this is shorthand for saying that there exists something in X, okay? Or there exists something in X such that something is equal to something, so something tautological. Then, provided, okay, that S has non-empty sets, there is an F will represent this function, such that for all X in S, there exists a Y with a property that the ordered pair XY is in F, okay, and this is shorthand notation that we can explain. I won't explain right now, but you can see it written down over here. And the pair XY satisfies, first of all, that Y is unique for every such X. How do we say that? We say that for all Z, if X comma Z is in F, then Z must be equal to Y. So there exists a unique Y. And secondly, what we want to choose is we want to choose an element of X, so this Y better be in X. Okay. And this is the formal, precise statement of the axiom of choice. Okay, so it was, for long, it was an open question whether this was, first of all, even something that could be proved from the other axioms of ZF, or something that could even be disproved for the axioms of ZF. So it turns out that neither of these two statements are true. So the axiom of choice is independent of ZF. Namely, it was Gödel in 1938 who showed that ZF does not prove the negation of the axiom of choice. The way that this was shown was by constructing an appropriate model of ZF, the so-called constructible universe, which was also not only a model of ZF, but a model of ZF and the axiom of choice. Okay, and Cohen, later on, in 1963, showed the other side of independence, namely, he showed that ZF does not prove the axiom of choice. So this was much more involved as a proof. And in order to show this, Cohen developed the technique of forcing. And this is something that you will see much of, and in fact you will learn about this if you take the forcing and the continuum hypothesis course, which I think you should do because it should be very interesting. Okay, so nonetheless, despite the fact that in general the axiom of choice is independent of ZF, the existence of a choice function can indeed be proved in ZF for certain specific cases. So for instance, if our family of sets contains just singletons, then clearly there's always a choice that can be made. Namely, you choose the element that is in the singleton. Moreover, it is also trivial, or at least reasonable, that if the collection of sets is finite, then there's always a choice function, and this can be shown in ZF. Finally, if there's some way that we can distinguish the elements of S by a relation, and I don't mean the elements of S, what I mean is distinguishing the elements of X where X is one of the elements in S, then this can also be shown. Okay, what I'm saying is a bit abstract, but suppose that there was an order on each one of these finite families, or on each one of these sets X, then of course you could always, there would always exist a choice function, which would simply tell you, for instance, take the least such thing. Okay, if there was an order for every such X in S, then you could just say, as a choice function, take the least thing. Okay, so if there was a way, for instance, to distinguish between two socks, which, assuming that the socks do not have labels on them, you can't do this, then there would exist a choice function even in ZF. Okay, so let's see a few equivalent statements. So I'll explain these slightly informally, but of course you can see how to express this more formally again, properly in the language of set theory. So a set X is said to be well ordered by a binary relation if this relation is a total order on X, meaning that it is transitive, it is irreflexive, and it is antisymmetric, with the property that every non-empty subset now of our set X has a minimal element with respect to this total order. Okay, so there exists some, for every such non-empty set S, there exists some S, small s, and capital S, such that for all t in S, S is less than or equal to t. Okay, because possibly t could be taken to be S itself. So for instance, the natural numbers are well ordered with a standard ordering. This is, it's very easy to see this because if you take any non-empty subset of the naturals, then it has a minimal element. Okay, that is trivially true. The rationals, on the other hand, are not well ordered. Well, they're not well ordered because they don't even have a minimal element themselves. Okay. What the well ordering principle, though, tells us is that it's the following statement. It says that every set may be well ordered, meaning that for all sets X, there is some binary relation on X that is a well order on X. Okay, this again is a statement that can be formally written down in the language of set theory. I will not bother to do this now. But what is very interesting and very nice, and it might be possibly slightly counterintuitive, but maybe not so much once you see the proof, is that under the rest of the axioms of ZF, AC, so the axiom of choice, is equivalent to the well ordering principle. Okay? So the axiom of choice looks like something that should be trivially true. On the other hand, the fact that you can well order any set whatsoever seems like something that is more counterintuitive, right? How can you always define, say, an order on the rationals that is a well order? Okay, well, it turns out that you can. Well, it doesn't turn out that you can, it turns out that this is equivalent to the axiom of choice. Okay, let's see another equivalent statement to this, which is one that is very commonly used in practice. So a partially ordered set, P, fix a partially ordered set, then an element in this partially ordered set is maximal if there's nothing else such that our element is below it. Okay. Moreover, a non-empty subset X of the poset P if you take a non-empty subset of our poset and you take some element B, then B is an upper bound for our non-empty subset if for all elements of X, this non-empty subset, it holds that X is less than or equal to B. Okay. Recall, by the way, because our poset only has a less than relation, less than or equal simply means what you would expect. It's less than or equal. Finally, a subset of a poset is a chain if it is totally ordered by the less than relation. Okay, so the following statement is known as Zorn's lemma. So what it says is that if P is a non-empty partially ordered set such that every chain in P has an upper bound, then P has a maximal element. Okay, so Zorn's lemma is perhaps maybe the one of the three, I guess, that I've described so far that looks like the most possibly random or most indeterminate. But it turns out actually that in ZF, choice is equivalent to Zorn's lemma. And in practice, as I was explaining before, Zorn's lemma is precisely the way that choice is most often applied. Okay, let's see some consequences of the axiom of choice that maybe you have already been assuming in most of your other courses. So a consequence of the axiom of choice, which is in fact even equivalent to it, is that every vector space has a basis. Okay, this is something that sounds fairly reasonable, and so it sounds fairly reasonable that one should be able to prove this in his axiomatization of mathematics. Another consequence is that every non-zero commutative ring has a maximal ideal. So this is something that you have probably shown in commutative algebra. On the other hand, a slightly counterintuitive consequence of the axiom of choice is that there is a non-Lebesgue measurable bounded subset of the reals. So this can be constructed using choice. Another consequence is that every connected graph has a spanning tree. And a point that I want to make before I finish off this video is that both the large cardinals course and the forcing course will be assuming the axiom of choice. And therefore, in the remaining of these videos, and in fact in all the logic courses you will be taking, choice will be assumed. So that's I think that's an advantage. So finally, ZFC, as I said in the beginning, is simply ZF plus the axiom of choice.